All right, the second TEK we're going to be going over now in forces is going to be 8.5 or 8.6b, which is speed, velocity, and acceleration. So we'll go over a couple of vocabulary words. First of all, motion is a change in position. So change in position, you see a skateboarder out your window, you look down, you turn around, and then they've moved. That's a great example of changing in position. So speed tells us the rate at which an object is moving. However, we use a formula for that. And here's your formula. Speed equals distance over time. You can use a triangle for this just because it's, triangles are really easy for understanding what formula you need to do. So for example, speed equals distance over time. So D is the top dog here. You're going to take D and put it in the house. And then you'll have either S or T, whichever one whichever one they give you, because the other one will be the X. So if, in this case, if they give you speed, X is going to be time. So you're going to be dividing distance by speed, and your answer will be the time. So that's kind of how this goes. And how you use the triangle is, if you want to calculate speed, you cover it, and then you know that you're going to be dividing distance by time. If you're trying to find distance, you're going to be multiplying speed by time. If you're trying to find time, you're going to be dividing distance by speed. And that's how you use the triangle. Excuse me. We are live. So, the triangle's great for a lot of different formulas. And so the other thing that can be interchangeable, and I'll talk about that in a second. Let's move back over to your vocabulary words. So that speed is velocity. Velocity and speed, when you're doing from a math standpoint, are exactly the same. You'll calculate them the same. So let's go back to the triangle. Instead of having speed, you'll have velocity here. So if you're trying to find the velocity, just replace V for S, and then you can use the magic triangle. That's how closely related speed and velocity are. In fact, speed and velocity are the exact same thing, except for one difference, is that speed, you just are finding, it just gives you the distance and the time, like 60 miles per hour is a speed. But if you want to turn that into a velocity, all you need to do is add a direction. So speed, it would be 60 miles an hour, turning that into a velocity, 60 miles per hour east or north or west. So velocity tells us the speed and the direction of an object. And the speed tells us the rate at which an object moves. So make sure you can differentiate between the two of those. And then acceleration, as you found out in the previous forces video, is the rate at speed or the direction changes that occur. So speeding up, slowing down, and or changing direction. So if I'm driving on the highway and I'm going 60 miles an hour and my speed doesn't change and I want to change lanes, so I'm going to put on my blinker, I'm going to stay 60 miles an hour, I'm going to turn my wheel just a little bit to get in the other lane, then I'm going to turn it back. I accelerated the moment I started turning my wheel. So remember, for acceleration to occur, we're either going to change our speed, speeding up or slowing down, or changing direction. So you can have a constant speed, but if you're going on a turn, driving on a turn, like on a windy road or whatever, you are accelerating. So those are your key vocabulary words for this, this TEK. So that brings us to graphs now. So when you have your graphs, you have distance on the y-axis and time on your x-axis. when you draw a line, a flat line or a horizontal line, look at your distance. You can see that the distance is not going up and down. The distance is staying the same. So if the distance is staying the same, we are at rest. In fact, you can do it a little something like this. I drove to work today. Let's say I drove at a constant speed. My line would move up like this. I stayed at work for 8-9 hours. My distance didn't change, and then I returned to home, back to 0 again. So that's what it would look like on a distance time graph. So constant speed is a line like this. Straight line, kind of at an angle. So this would be a constant speed. If the line was a little bit lower, going straight, it would be a slower constant speed. If you're in a spaceship, if you're flying at light speed, your line is going practically straight up. But super fast constant speed would go like this. You're traveling a great distance in just a little bit of time. So whenever you're looking at these distances, and if you see a line that goes here, a line that goes here, and a line that goes here, remember this, the first line that hit the distance at the closest time would be the winner of that race. So that kind of shows here, you have the broken line moving at a much faster constant speed, and then this line moving at a regular constant speed, for example. And we have acceleration, speeding up. You can do the line like this and going like this way, and that would be acceleration as well. Slowing down. Starting off really fast and then slowing down. So this is a summary. This is actually a page that you guys are going to be doing when you get to motion graphs. So yeah, so I'm kind of giving you some explanation. This is a wonderful, wonderful example of speed on a distance time graph, and know that stationary or at rest is a flat line on a distance time graph, and then returning to start. Some other explanations there, but I hit you with the basics. There's something, and then you're gonna, show your work. Now let's move on to what if you change the y-axis to speed, and now we have a speed time graph. The information on a speed time graph is different. Remember that flat line on distance time where that was at rest? Well, a flat time on a speed time graph is constant speed. So you can see that the y-axis tells the story. You can have all these lines on the graph, but the y-axis will completely change that story. So it is critical that you identify what is on the y-axis when you're looking at graphs and you're trying to match a graph with a story. Know where your constant speeds are. Know where your at-rests are on a speed time graph and a distance time graph. If you can identify those, chances are you will be able to answer the STAR question. So let's just finish looking at these lines really quickly. Speed time graph. Now we're looking at that line again, the one that showed constant speed on distance time now is showing acceleration. Do you see that the object is accelerating at a constant rate? That's what's happening here. Because it's a flat line on a speed time graph, it is accelerating at a constant rate. Versus if it was bent like this, it would be just acceleration. But this is constant rate acceleration. This is also acceleration when you're slowing down. Remember, the definition of acceleration is speeding up, slowing down, and changing direction. So this is deceleration at a constant rate, but it's also defined as acceleration. The dashed line shows greater acceleration, regular acceleration, and then a line like this would be slower acceleration. And here is another great example of speed time graphs. So that was it. That's really it for 8.6 B, understanding and being able to differentiate between speed, velocity, and acceleration. For this TEK, you will be looking at graphs, you'll be calculating, you'll be using the formula and trying to understand graphs. So knowing the vocabulary words inside and out, being able to differentiate between speed and velocity, and then being able to read a distance time and speed time graph is what you need to be successful on this TEK. All right, guys, we'll see you in the class. Thanks.